Supposing you have two random variables jointly defined with a joint PMF or joint PDF. Or discrete, does not matter, jointly continuous or discrete. Remember, in the case of a discrete PMF, the computation always involves a sum, and in the continuous case you have to do an integration, right. Then I can directly write out using the Lotus theorem, right, or Lotus itself is a law, right. So, using Lotus, this E of a single scalar function of two random variables. So now I am just taking a scalar real valued function g of xy, which could be x plus y, could be max xy, could be anything, but as long as it is single scalar valued function, single real valued function, right. So this is basically in the discrete case, it is basically this sum. So over all allowed pairs xy in omega xy, I think this may not come so clearly in the recording, but can't help it. So x comma y. So that means that you are doing the integral, the sum over all points in the in the space omega xy. Then of course for the continuous case, what do we do? How do I write it out? Right. So g of xy, the joint and PDF. Again these quantities on the right hand side make sense if and only if the absolute value, what you get by putting the absolute value, the result is finite. In other words, provided E of mod gx, the absolute value of this function is finite. So of course there are some other random variables pairs, which this is not right the most general formulation, but for more general formulations we need to use some crazy notation and all that, which have not introduced at all. So as of now we have only stuck to both of them, either jointly discrete or jointly continuous. So we only give the results for these two cases. Likewise, I already mentioned in the case of single random variable that the formulas that we have written do not easily apply to the so called mixed, which is, I do not like the term, but I do not know what else to say, not or a random variable x with a CDF with jumps, right. You cannot so easily write down a simple expression for the mean, and leave, you can't do it for the mean, then the means variance also becomes quite or the E of x squared also has problems. Likewise here again, right, you can come up with random variables which are neither purely discrete nor purely continuous, right, and it's, only in some cases you can easily write down the an expression for E of xy, but in all the examples we have done, we for jointly discrete, jointly continuous, these expressions will be valid. We have done so many, for example, trinomial for the jointly discrete case. The jointly discrete turns out is a more easy to understand and appreciate always, right. So you should always base your understanding on what happens with multiple random variables. You think about the jointly discrete case where you only have a set of points, right, and then try to generalize to this. So let us see now again some properties of writing this average. Again the meaning of the expected value is identical to what we had, what we had in the single random variable case, right. So this will be, or it tries to model an average of this function g over many independent observations of the pair xy. X and y can be the height and weight, for example, right, correlated, and you could model that as a continuous pair. So now if I, I'm not sure if I can call the set of people in this room as independent, but anyhow, so if you wanted to average all those values of right, some function g of xy, some linear combination of height and weight, for example, you could what you get here is basically a model for going and looking at each person and doing that calculation of that person, then averaging of the whole lot. Okay. So the meaning of E is always an average, a statistical average, no matter how you define it. So that brings up the question, is this E now that we have defined here, is it consistent with the, supposing you have only x, what if g of xy is xy, as we said, as we saw in the context of transformations, right, you can always define g of xy to be x. So suppose supposing I just take this, is this definition consistent with what we wrote earlier, in the sense of, do they both give the same Ex? What would be your answer to that? Yes, they give the same answer. Why? Because if I do this, for example, let us say I take the continuous case. Now let us say I write this as dy dx, not as dx dy. Say that there is a nefarious reason for writing as dy dx. Why? Because I want to integrate over y first and then over x. What is the value of this integral? If I first integrate over y keeping x fixed, then obviously I have to integrate over the limits that are imposed by that value of x. So this will be an integral over omega x of what? X times the marginal. So you integrate over y. Keeping x fixed. Remember, I said in my very first lecture that you must be very clear about multivariable integration, right? And I think you have done enough examples in some homeworks to appreciate this. So without taking any specific examples, I can always go from here to here, can I not? If I integrate with x fixed, that is this integral of this for fixed x is always the marginal density by definition. And what is this? This is Ex as per earlier definition. So the E operator is always consistent, and the same thing you can apply to higher density, higher dimensional density functions also. So in other words, the scope of the E operator is basically defined by by what is operating on. If there is only a single random variable inside the G, then you understand that to be basically involving only the statistics of that random variable. If you have a function of two random variables, then it is the joint distribution of those two random variables, and so on. So E, you write the same E no matter what. I am not going to put a subscript here on E right now. Maybe later on in some cases I might write a subscript to not for expectation of this kind, but for conditional expectations, just to keep things straight. I might put a subscript here to indicate the scope of that E, but for this it is not required. Okay, so E is consistent. We are very thankful for this, because if it were not, then the whole theory pretty much would collapse, right? The E would almost be meaningless if it were not consistent. So no need for, at least at this stage, no need for subscripts. And if it's jointly discrete also, I don't think there's any issue here, right? There you don't even have an integral to worry about. You just have x of pxy. You sum over y, you know automatically you get the density, the PMF of x at that value small x. So then it's exactly the same as before. Okay. So then what is the this is the right, we did this only to show the consistency. Okay, now keeping that, let us take some other example of g of xy. The most useful example of, or among the most useful examples of g of xy is x plus y, always, right? This is extremely important, because this is a kind of linearity of the E operator that we did not encounter in the first version, which is with the single random variable. So what happens if I substitute x plus y here or here? What do I get? Please do it and tell me. Huh? What do I get? You're saying something which I cannot understand. Huh? No. Expectation of x plus, now I heard you. Expectation of x plus, E of x plus E of y. It's a crucial result which does not, which holds universally as long as both of these are finite. So the linearity of E takes on yet another meaning now. It's not just g1x plus g2x that we did earlier. Instead, now we have x plus y, two totally different random variables, and still you get. So for those of you that are still saying, so all I am saying is you take either formula and substitute x plus y. It turns out by the distribution of multiplication over summation, right, it is x times this plus y times this, and then the summation, if you do it twice, once for the x and once for the y, as I just did and I erased, right, you will get Ex in the first term and Ey in the second term. So please go and work out the details, get for this. So you do not require x and y to be independent, so it is very general. No independence assumption. Right. Likewise, we also have E of x minus y to be Ex minus Ey. And this obviously is mx plus my, because right, there is only one Ex and that is mx, right. Okay. So how do I now go, put this result to work? What do I need to, yeah, huh? Okay, yeah, of course, we can extend this to any linear combination, E of sigma ai, if that is what you want, ai, let us say I have a collection of random variables. Yeah, now that you mentioned it, let me write it. Supposing I have, let us say, some k random variables or something. They can be dependent, independent, I do not care. So this will be equal to, sorry, so this weighted combination, right. So I do not, what I am trying to say here is, this may look like a complicated thing, which is in fact a complicated thing. If you want to calculate the distribution of, exact distribution of this, right, it is not easy in general to find, right, the PDF or PMF of this quantity, of this weighted sum. Even here, you had to do a even when x and y are independent, you have to do some convolution and stuff like that. It's not the simplest of things to do to determine the actual distribution. But it turns out if you are just looking at the mean and the variance also is not too difficult to calculate, right. Turns out just the mean here, the mean of this weighted combination is just this weighted summation of the means, and no independence again is required. X1 through xk can be an arbitrary collection of random variables on some space, right. Okay, now that we have done this for the okay, and also one other thing, right, this quantity depends only on the means. So it turns out in practice these means are easy to estimate, because the means only involve just the PMF of just that one random variable and not the others. So in multiple ways this result is very useful.